Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We're very happy to have Xin Li from University of Washington with us today. Xin got his PhD working with Professor David Zuckerman at UT Austin and is now a Simmons postdoctoral fellow at the University of Washington. He's done a lot of very nice work in the area of randomness extractors and its application to cryptography, and he's going to be talking to us about privacy amplification and non-malleable extractors. Thanks a lot, Xin.
Thank you. Right. Okay, so this is a joint work with Yevgeniy Dodis, Trevor Wooley, and David Zuckerman. The title is Privacy Amplification and Non-Malleable Extractors via Calculated Sums. Okay, so let me start with the introduction of this problem. So first, the setting is that you have two parties, Alice and Bob, standard, and so they share some random string, but the random string is not uniform. Instead, it's just some weakly random strings, which I'm going to define formally later. And to notice that this string is secret in the sense that it is not known to the adversary heap. So the adversary heap who is watching this channel. And we're also assuming that these two parties have local random bits, which are private in the sense that the local randomness is also not known to the adversary heap. So what is this problem? The problem is basically that two parties in the presence of this adversary heap, they want to somehow communicate with each other such that at the end of the protocol, they want to agree on shared uniform and private random strings. So these two strings are they're going to be the same for both parties, and they are supposed to be uniform and private in the sense that these strings are still not known to the adversary heap. So that's a basic setting. And in this talk, also in our work, we're assuming that heap is computationally unbounded. So if heap is computationally bounded, then we can somehow use the standard cryptographic primitives to deal with this problem, but we're not assuming that. Instead, we're assuming that heap has unlimited computational power. So this framework is basically purely information theoretic setting. All right, so as I just said, we're assuming that the two parties share a weakly random string, and the formal model for some weak random string is called the weak random source. So basically, if we have an n-bit string, then the weak random source is just some random variable or probabilities distribution over the n-bit strings. But then you need a way to measure the entropy of the weak source, which we were going to measure it by the now standard notion of mean entropy. So it is simple that if source has a mean entropy k, then basically it's saying that for any element in the support, the property that the random variable takes this support is at most 2 to the minus k. And for this talk, and also for most of the applications using weak random sources, you can just simply think of the weak random source to be some uniform distribution over some large subsets, which has size at least 2 to the k. So yeah, so that's going to make our analysis simple. So just assume that the source is a uniform distribution over the subset A.
Can you always go from an entropy to this, to a flat source?
I'm sorry?
Can you always go from an entropy source to a flat source?
Yeah, the thing is that every weak source with mean entropy k is actually a convex combination of flat sources. Okay, so as the title suggests, I'm going to talk about randomness extractors. And so what is a randomness extractor? So basically, it's supposed to be some algorithm that that is giving us an input some weak random string, weak source, m bits with some entropy k, and the algorithm is supposed to output, say, m bits that is supposed to be uniform, but we allow the outputs to have some small statistical error. And the error is just the L1 norm, or the statistical error, or the variation distance. But the problem is that if we want the extractor to be a deterministic algorithm, then this task is actually impossible. Even if the weak random source has entropy something like m-1, and even if you just want to output 1 bit, that is impossible if we want the extractor to be a deterministic algorithm. So then, given the negative result, so there are several different ways to attack this problem, and one of these is what we now call a seeded extractor, which is introduced by the paper in the paper by Nielsen and Zuckerman, and then subsequently studied in many research papers. So here now the extractor is not a deterministic algorithm. Instead, it is a probabilistic algorithm, in the sense that it is also given a small random seed, which we will call y, that has d bits. The seed is going to be independent of the weak random source. And then with the seed, you can output, indeed you can output some m bits with small statistical error. And the goal here is that you want this number of bits d to be much smaller than the length of the seed. So generally we would want this d to be something like order log n, if this epsilon is some constant. So this kind of object city extractors have been studied a lot. And now we have nearly optimal constructions of these kind of extractors. And we were also going to need the notion of a strong extractor. So basically, this is saying that not only is the output distribution close to uniform, but it is also close to uniform even if you are given a seed y here. So basically, this is saying the joint distribution of the output and the y is close to a uniform distribution. Okay. So given the previously strong extractor, here is a protocol for the privacy amplification problem, where the adversary is assumed to be passive. So by passive, I mean that the adversary is only allowed to watch the messages transmitted between the two parties, but she is not allowed to change the messages in any ways. So in this setting, there's a simple protocol using strong city extractors. So the protocol is that first you have Alice pick some uniform random seed y from her own local random bits, and then Alice just send this string to Bob, and then they just apply this strong city extractor. This. They both apply this strong city extractor. And the claim is that they're going to end up with some shared uniform and private random string. And why is this the case? This is only just because that the adversary cannot change the seed. So both Alice and Bob get the same seed y. And now they apply the extractor, and because it is strong, which means that even if you condition a seed y, the output is close to uniform. And also because here the only information that you can get is the seed y here. So even condition on this, the output is close to uniform, which means that basically they're private to the adversary. So that is a simple protocol. But if you think about it, if now we allow the adversary to be active, in the sense that she can indeed change the messages, then the above protocol actually fails. And it fails for a simple reason, because the adversary can change this random string y into something else, y prime. And then if you apply this strong extractor again, then these two outputs, they may no longer be equal to each other. So in this case, the protocol fails. Right. So now more specifically, what do we mean by an active adversary? So it is a very powerful adversary in the sense that the adversary can somehow arbitrarily change, insert, delete, modify, and reorder the messages. And for example, the adversary can first run several rounds with one party before it decides to resume execution with the other party. Meaning that in this sense, the protocol may not behave synchronously between the two parties. So here indeed this active adversary is a very quite powerful adversary. And in this talk as well in our work, we're assuming that the adversary is active. So we're trying to deal with this kind of adversary. Okay, so here is a formal definition of a privacy amplification protocol. So here we're assuming that we have an active adversary. And so in the end, the two parties, Alice and Bob, they are supposed to output some strings, but they can also output some special symbol here. So this symbol just indicates that this party will reject a protocol. And for the privacy amplification protocol, we will require the protocol to have three properties. So the first is that it's called correctness. So this is simple. This just says that if the adversary is passive, then with property 1, the two outputs of the two parties are the same, and they are not equal to the rejection symbol here. That's actually quite intuitive. And then robustness, which says if Eve is indeed active, then the property that Eve can corrupt the protocol is small. So what do I mean by Eve can corrupt the protocol? So Eve can corrupt the protocol if she manages to somehow make the two outputs RA and RB not equal to each other. And also they are not the rejection symbol. In this case, we will say that the U actually corrupts the protocol, and we want that the property that U can do this is small. And then the third property is just the extraction property, which says if with high property a party does not reject, then his or her output is going to be close to uniformity, even in the adversary's view. So that's actually the goal of the original goal of the protocol, to to convert the original weak random source into a uniform string. Okay, and now we have the two parameters that are of particular interest here. So first of all, this k minus m. So m is the length of the output. K is the entropy of the original weak random source. So k minus m is the entropy loss of the protocol. And we also have this parameter epsilon here, and we'll define S, which is log 1 over epsilon, to be the security parameter of the protocol. Sure.
Lessness property, can you guarantee that one of them? So here you're allowing one of them can get the uniform string, and the other one gets bot, and that's okay. Can you also call it bad if, say, A outputs?
If one of them, if one of them gets a uniform string and then the other gets bottom, then that is okay, because the other party actually rejects the protocol.
So can you make it so that one person sort of always knows if the other person's protocol fails?
One person always knows the other person fails.
A always knows B's protocol. If B outputs bot, for example, so then A would but maybe not the other way around.
Yeah, it may not be this case. Right.
Always block the last message.
Right.
So I see that you maybe A doesn't know. So A doesn't know if B got the last message, but B should always know that A got the last message. So
One way might be
yeah, so
that's right. Yeah.
One way.
Right, one way is
half of the properties.
yeah, that's right.
Thanks.
Okay, so any other questions? Is it clear about the definition here? Okay. Right. Okay, so now this table shows some of the previous works here. So remember S here is the security parameter. So basically, the ultimate goal of the privacy amplification protocol is that you want to get a protocol with a small number of rounds as possible, and you want to get a small entropy loss as possible. So, of course, here the first result due to Morrow and Wolf in 1907. I guess one round protocol, which is pretty good, but they only work for entropy rate. Entropy is something like k is greater than 2/3 of the n. And the entropy loss is pretty big, so something like m minus k. And then this protocol is later improved by these authors, by Dodis and Case, Raising, and Smith, I guess, to work for the case where entropy is greater than n over 2. But the entropy loss is still big. It's one round here. And just to note that there is a negative result by Dodis and Wichs in this paper, which basically shows that if this entropy k is smaller than n over 2, then there is no one-round protocol. So in that case, the best you can get is two-round protocols. Okay, but the first protocol that breaks this n over 2 barrier is due to Riner and Wolf in 2003. So they actually gave a protocol which can essentially work for any entropy here. But it would require something round, something like this, s plus log n. And the entropy loss is s plus log n squared. And then there is also a slightly simplification and by this paper of Knukthi and Raising. But the parameters are essentially the same. And then there's this paper by Dodis and Wichs, who reduced the number of rounds to 2, but the entropy loss is still s plus log n squared. And then there's this paper by here and also these four authors who managed to get the entropy loss to something like s plus log n. But then the number of rounds blows up to also something like s plus log n. And just note that the optimal protocol, who is provided in this paper by Dodis and Wichs, but is non-explicit. So they show that non-explicitly you have this optimal protocol, which can achieve 2 rounds, and you have optimal entropy loss s plus log n. So all of the previous results, they can just only achieve optimum in just one of these 2 parameters. You can achieve the 2 rounds, but then the entropy loss is bigger. Or you can achieve the optimal entropy loss, but then the round is bigger, s plus log n. So the open problem is that if we can achieve optimum in both of these parameters. And in this paper by Dodis and Wichs, they showed that these optimal results can actually be achieved by using something called a non-malleable extractor. So which I'm going to talk about later. So these are the previous results. Okay. So what are our results? Basically, in this paper, we give 2 improvements of the previous results. So in the case where the entropy is bigger than n over 2, so we get a 2-round protocol. So recall that indeed you have 1-round protocol, but the entropy loss has to be much bigger, n minus k. So here we get a 2-round protocols, but we get optimal entropy loss, s plus log n. And then In this case, where you only have, like, say, any constant C, so here the delta is any arbitrary constant. So in this case, if you have any delta and entropy here, then we actually get a protocol that is pretty close to the optimal result. We get a constant number round protocol that also has entropy loss, S plus log, optimal entropy loss, S plus log n here. Yeah, this constant depends on this delta here. But as long as delta is constant, this is also a constant. Okay, so we obtain these two improvements by constructing the first explicit non-malleable extractors. So in the rest of the talk, I'm going to first talk about the non-malleable extractors construction and say a few words about the proof. And then I'll talk about the private amplification protocol for this entropy rate delta and where delta is any constant. I'm also going to say a few words about this two-round protocol, which is actually a direct corollary from the result of Dodis and Wichs. Right. So now, what is a non-malleable extractor? So it is defined in this paper by Dodis and Wichs. So I'll first start with a seed extractor, as you have seen before. So this is simple. You just have an extractor. You have a seed and output, and the output is supposed to be close to uniform. So here, this notion just means that this output has error, statistical error epsilon from the uniform distribution. And then, so this is a seed extractor. So a stronger notion of the seed extractor, which you have also seen before, is a strong seed extractor. Which requires that even if you're also given the seed y here, the output is still close to uniform. So now the non-malleable extractor, in a way, you can just think of it as an even stronger notion of the strong seed extractor. So here you're not only given the seed y, but you're also given an output of the non-malleable extractor on some correlated seed AY here. So this AY is assumed to be not equal to the original seed Y. But except from this AY could be arbitrarily correlated to the seed Y. So now we require that even if you are given the seed Y and also you are given the output of the non-malleable extractor on the arbitrarily correlated seed AY, the original output of the extractor is still close to uniform. Sense. and just as a note that the output cannot be bigger than the entropy over 2 here. Okay, so is this definition clear? Any problems?
Can you explain it again? Sorry. So, if some information is already leaked about y to the adversary A.
Yeah, actually the seed y is completely leaked to the adversary.
Right. So then. Okay, but y was chosen uniformly before.
Yeah, y was chosen uniformly before. And the adversary can also choose another C AY, which is not equal to y. But except this condition, he can choose whatever he wants. This AY could be arbitrarily correlated to this seed y. And then the adversary also gets the information of the non-malleable extractor's output on this seed AY here. Which means that she actually now gets two kind of informations. It gets this seed y, it gets this output on another seed AY. And we're requiring that even if the adversary gets these two informations, still the output of the non-malleable extractor on the original seed y is close to uniform.
So basically you're saying that it's just like a strong seed extractor, but now even if the challenge for the adversary is to output another random string from using the extractor so that the two outputs are correlated, and he cannot do that.
Right.
That's what you're trying to say.
Yeah. So it's actually much stronger than the strong seed extractor. in the sense that the adversary gets another output here.
So in one case you're taking the uniform, the output of the actual extractor. In the other case you're looking at the uniform. And if they were correlated in one, in the other they are not correlated because the other thing is uniform. So they cannot be correlated. And that's the challenge for that person. You cannot do that as Wichs definitions. Am I right?
Sorry, can you say that again?
Okay. So think of this as a game, right?
Yeah.
Where the adversary is supposed to output a string whose output looks correlated to the output of the extractor.
Yeah, that's right.
And he can do that. Because in the second experiment, the output is uniform, so they will never be correlated. Whereas in the experiment on the left, it's the actual output of the extractor. So if they are statistically close, then they are not correlated to each other. That's why it's not really.
Yeah, right.
Not even just output, you can't even distinguish from it. Outputting is much stronger. Here it's, I mean, it's
No,
a much
so-
weaker requirement for the adversary,
Yeah,
what
yeah.
you're saying. Here it's stronger.
No. If you want non-malleability, then you need a statistical distinction. So when you were saying that they are statistically independent. They could have been computationally independent. That's fine too, right? But the statistical independence.
Right, but here
means that they are.
Here we are considering the information theoretic setting, so we're considering the statistical distance. Yeah. Okay. Any other questions? Fine. Okay. Okay. So just to give you some sense of the non-malleable extractor, here's a negative example. So if you consider this extractor, which is just the inner product. So you take a source X, you take an independent seed Y. So here this Y has the same length as the source. And you just take the inner product over the field F2. This is actually a very good, strong extractor. So it actually works for essentially any mean entropy here. But it turns out it is a very bad non-malleable extractor. So it is not a non-malleable extractor, even if the entropy K here is something like m-1. So to see this, you can consider this source X, which has the first bit fixed to be 0, and the rest of the bits are just uniformly distributed. So you can see that this source has entropy m-1. But now this adversary giving any seed Y, he can just make this AY to be the string that has the first bit of Y flipped, and the rest of the bits are the same. And then you can see easily that X inner product with Y is always the same as X inner product with AY here. So which means that this extractor, despite it's a very good, strong extractor, it is a very bad non-malleable extractor here. So which somehow suggests that the task to construct a non-malleable extractor is not a trivial thing. Okay. So in this paper by Dodis and Wichs, they showed that if you can construct non-malleable extractors for entropy K, then you can actually give optimal protocol privacy amplification protocols for essentially the same mean entropy. And they managed to show that such kind of non-malleable extractors exist. So if you think about it, it's not even clear that these kind of things exist. But they show that these kind of things actually indeed exist. And they show that you can use the seed length D, something similar as in the seed extractor, something as small as log n here. And then you can extract up to something like m equals to k over 2. If you just ignore the others thing, you can extract up to k over 2 bits. But they didn't give any constructions of explicit non-malleable extractors. They only constructed some weaker forms of non-malleable extractors. But I'm not going to describe this. Okay. So in this paper, we give the first explicit non-malleable extractor. Before our work, there is no known explicit constructions of non-malleable extractor for whatever parameters. So so this non-malleable extractor we construct works for entropy greater than n over 2. and it uses seed length, and so the seed length is the same as the source, and it outputs something like k minus the number 2 bits. So if this k is say n over 2 plus delta, and so then in this case we can output a linear number of bits here. But if we want to output more bits, we want to output more than log n bits, then the efficiency of our construction relies on some conjectures about primes in arithmetic progressions. But I'm not going to get into the details about this. It's just some well-known conjectures. So as a corollary, we get this to round privacy amplification protocol. If we assume this conjecture, so this is a direct corollary of the result of Dodis and Wichs. And then we using this non-malleable extractor, even if it only works for entropy greater than number 2, we managed to get a new protocol that runs in constant number of rounds, and we get also optimal entropy loss. Okay. So there's one very nice subsequent work here, which is by Cohen, Rasmus, and Yep, who also give a construction that works for entropy greater than n over 2, but they can use a small seed length. Indeed, they can use something like log n, but their output is actually smaller than the seed length, which means that if you want to output a large number of bits, then the seed length is forced to be large. And also, their construction does not rely on any unproven assumptions. So in fact, our construction can be viewed as a special case of their construction. And also, after seeing their nice paper, we actually showed that our original non-malleable extractor works even if the seed is not uniform, even if the seed only has some mean entropy, something like m plus log n times some constant here. And this again turns that we can also achieve a small seed length as in their construction. But this work is only done after we have seen their paper. Okay. So now I'm going to talk a little bit about our construction of the non-malleable extractors. So if we want to output 1 bit, then the construction is actually simple. It's just the Paley graph construction over some finite field FQ here. So to be more specific, so we like chi s here to be the quadratic character. So if chi s, if s is some square of some element, then it's 1. If not, then it's -1. If s equal to 0, then this is 0. Of course, you can very conveniently convert this +1, -1 into 0 and 1. And also to note that this quadratic character is a multiplicative character, which means that chi s times t is chi s times chi t here. And now our extractor here is simple. You just take a source x, you take an independent seed y, and you compute the quadratic character of x plus y over some field FQ here. And if you want to output more bits, then it's basically this extractor that has been studied before in this paper by Carr and Gojek. But they studied this extractor in the context of 2 source extractors. And we show that it is also a non-malleable extractor. So here we basically choose some prime that is congruent to 1 mod 2 to the m. And let G to be a generator in this field FQ. So the conjecture I mentioned before implies that such a prime Q can be found efficiently. And then the extractor is just the discrete log of x plus y mod some 2 to the m. So m here is the number of output bits here. And it turns out we can compute this discrete log mod to do them in an efficient way.
Does that also rely on the conjecture? Or?
What?
Does that also rely on the conjecture? Or?
No. This doesn't rely on the conjecture, but we need this. But the conjecture is just to find this prime Q. Okay, so
you require the conjecture only like one time, right? So you need to put in. So even if, for example, finding this prime takes time, you need to do that only once.
Yeah,
right?
that's
it's not for every application. Of
that's right. Yeah. Exactly. Okay, so now I'm going to say a few words about the analysis. So why this is a non-malleable extractor. So basically, to show that this is a non-malleable extractor, it's suffices to show that most of the C's Y. So first of all, this party is close to uniform. This is actually already follows from the party that this thing is a strong extractor. So I'm not going to go into the details of this, but this thing has already been proved in this old paper by Carr and Godric that this is a strong extractor. So the main part we need to prove is that so here is for 1 bit case, you want to prove that the XOR of these two things are still close to uniform. That means that this output is somehow uncorrelated with the original output. Yeah, and just this is essentially to the same thing as above, that you want to show the first party is close to uniform and that this XOR with this is close to uniform. So to prove this, so the main tool we use is a character sum estimate. So this is a little messy here, but the main thing is that so this S, you can think of as the support of the weak random source, which is a subset. And so the weak random source, you can think of it just as a uniform distribution over this set S. And this A is just the adversary function from FQ to FQ. So when you have Y, the adversary changes to some AY here. So basically, to show that basically, to show this thing, it suffices to show that this bound holds. So this is basically saying that for the sum over all C's Y, that so the XOR, when you convert it into the quadratic character, it basically is equivalent to the multiplication here. So basically, you want to show this. And the main tool to prove this is Weier's theorem. So basically, it says if f is a monic more polynomial over, let's say, with r distinct roots, and that is not a square, then the absolute value of the sum of the quadratic character of fz, when the z is over the whole field fq, is bounded. Is bounded away from q. So the trivial bound is something like q here, but here the bound gets much smaller, like something like q to the square root of q here. So using this, we could bound this quantity here. So I guess I'm not going to go into the details, but just let me skip this. So let me just say that in the end we can end up with estimating some quantity like this, and here this this H is basically a polynomial in S with degree 4, and so you can check that this H is a square if and only if y equals to z or y equals to az and z equals to ay. And then you can just divide into two cases, and you can bound this thing trivially by considering the two cases whether it's a square or it's not, and you get this bound here. And just note that if we want to analyze a case where you extract more bits, then you need to estimate this thing for any non-trivial characters, chi and chi prime. And to do that, we need some kind of non-uniform XOR lemmas. Okay. Okay. So in the rest of the talk, I'm going to describe those privacy implication protocols for entropy rate k equals delta n for any constant delta here. So to describe the protocol, I'm first going to introduce some cryptography primitive called the messenger authentication code, or you can just simply say it's a MAC. So what is a messenger authentication code? So again, here you have two parties, Alice and Bob here. But here we assume that instead of sharing some weakly random string, they share some uniform private string R here. And also they have, again, they have this adversary U, who is active, who is computationally unbounded, and who controls this channel between the two parties. So what does this MAC do? So essentially, so here Alice picks a uniform random string y. So this string y is chosen from her own local uniform random bits. And Alice sends this string y together with some tag t here. So this tag t is computed from this MAC by using this shared random bits r as a seed. So basically, the MAC uses a random seed r here to compute a tag t for this message y here. In this case, Alice can send y under tag to Bob. But as usual, the adversary U can change the messages into something else. You can try to change it into some y prime on t prime. And the main property that the messenger authentication code would want is that if the adversary U does not know the shared uniform string R, then the probability that the adversary can come up with a different string y prime, and can also come up with a correct tag t prime for this message y prime is going to be small. It's going to be bounded by some epsilon here. So that's main properties that we need for message authentication code. So is this clear? Any questions? Fine. Okay. And just to note that so this MAC works in the case where this R is uniform random. But just note that there are constructions of the message authentication codes which works even if this R is not completely uniform random. But if this R has entropy rate greater than half, then it still works. So entropy rate here just means the entropy divided by the length of the string R here. So we have this kind of MACs that works even if R is not completely uniform. Okay, so given the previous message authentication code, so here is a protocol for the case where the entropy rate is greater than half. So this is basically the protocol by Dodis and Wichs plus the construction of our non-malleable extractor here. So now these two parties, Alice and Bob, they share some nk weak random source. So this just means that the source has length n and it has entropy k here. So again, the first step is Alice chooses a random string y from her local random bits and sends it to Bob. And this could be changed by the adversary into something else y prime here. And then both parties are using this non-malleable extractor to compute outputs. So Alice computes the non-malleable extractor applied to x and y. Bob computes the non-malleable extractor applies to x and y prime. So they now get two outputs, r and r prime here, which may not equal to each other. And then in the next round, Bob would choose some w prime. So this is a uniform random string from his own local random bits. And then Bob will send w prime together with a tag t prime to Alice. And this tag is computed by using this output r prime as a MAC key to get a tag for his message w prime and send it to Alice. And of course, that Alice may get something completely different. He may get some wt here. And then Alice will just check the MAC. We'll check that if this tag is correctly MAC for this message w she receives. And if not, then Alice will just reject. Otherwise, if Alice does not reject, then she will compute these outputs. And Bob will always compute his own output, z prime here. So, so I claim that this is a privacy amplification protocol. And the analysis turns out to be simple. So just you consider two cases. So the first case is that the adversary if does not change the seed y. If the adversary does not change y, then y prime and y are basically the same, so which means that r prime and r are also the same. And also, since this non-malleable extractor is also strong city extractor, so this r prime and r are the same and they are private in Eve's view. And then, as I just said, by the property of the MAC, Bob can authenticate his message w prime to Alice. And the adversary, if he wants to change it to some wt, then the probability that Alice does not reject is going to be small by the property of the MAC here. On the other hand, if the adversary does change y, so if the adversary changes y into something different y prime, then the non-malleable extractor probably guarantees that this r prime is actually this r prime is actually independent of r. So even condition r prime this r is uniform. So then even if the adversary if she sees this MAC t prime, because this only comes from this output r prime, which is completely independent of r. So even given this information, the adversary cannot come up with a correct tag for this message w here, which means in this case, Alice will also reject with high probability. So basically, two cases: if the adversary doesn't change y, then the MAC guarantees that Bob can authenticate the message to Alice. If the adversary does change y, then the non-malleable extractor probably guarantees that Alice will reject with high probability. Is this protocol clear? Okay. So and then by plugging our non-malleable extractor for entropy rate greater than half, we get this two-round protocol. And just note that that all of these messages y this w and t prime has length something like s plus log n, so you get the optimal entropy loss protocol. Yeah. So the analysis, just like I said, is whether Eve changes this seed y here. Okay. So so then I'm going to describe this privacy amplification protocol for the case where k is equal to delta n. So it basically uses the previous protocols. So again, here you have Alice, Bob, Eve, and they share a weak random source here. So the first idea is that so we want to apply this non-malleable extractor for entropy rate greater than half. But here the source only has a very small entropy rate delta here. So the first idea is that we can apply something called a somewhere condenser. So what is a somewhere condenser? So basically, it's a deterministic algorithm that can convert this weak random source with entropy delta into a constant number of blocks. So this constant number, all the one here, depends on this delta here. But nevertheless, it's constant number of blocks, such that at least one of the block has entropy rate, say, greater than 0.9 here. And then, so you can see, so it's very natural that you can convert into this, and then you want to somehow try the previous protocols in some of these blocks where the entropy rate is greater than half. So indeed, the idea is that you want to apply this two-round protocol to every block. Okay. And then we hope that at some of the intermediate block where the entropy rate is bigger than half, the protocol will succeed. Okay, so more specifically, we're going to associate the phase of the protocol with each of the block. And we want the final protocol to achieve the following two goals. The first goal is that in the phase of the first good block. So by the first good block, I mean the first block that has entropy rate greater than half. So, so if in this graph, then this block is bad, and then this block is good. Then this is the first good block. So we want to say that in the first good block, so Alice and Bob will agree on a private uniform random string. So this is in this phase associated with this first good block. So at the end of this phase, the two parties agreed on some private uniform random string. And the second goal we want to achieve is that once this is done, then we somehow want to guarantee that in all subsequent phases, they continue to agree on some private uniform random string. And then if this is case, then we can just use the output from the last phase and the final output. Because here they agree on a uniform random string, and then they continue to agree on a uniform random string. Then, so at the end, they still agree on some uniform random strings. Okay, so let's see how we can achieve the first goal here. So, of course, if you think about it, then the first goal is to achieve to have the two parties agree on a uniform random string at the first good block. The first good block already has entropy rate greater than half, but the messages sent before the first good phase may leak some information about the first good block. So it may not have entropy rate greater than half. But the solution is that we can limit the size of the messages sent before the first good block. So as long as the security parameter is not too large, we can limit the size of the messages so that, because you notice that there's only a constant number of blocks, so there is at most a constant number of rounds. So you can limit the size of the messages such that, because the size of the message is small, so the information leaked is small. So you can guarantee, even if you condition all the messages sent before, the good block still has entropy rate greater than half. And so in this case, we did, and then plugging the previous two-round protocol for entropy rate greater than half, we guarantee that we achieve the first goal. That at the end of the phase of the first good block, the two parties will agree on some uniform random string that are private to the adversary. Okay, let's see how we can achieve goal 2 here. So here is this graph shows a particular phase. So the face is for the block xi here. So this shows something after the first, after the face of the first good block. So here this xi has say entropy rate greater than less than half. So as the picture shows. So this is exactly the same protocol, the same two-round protocol as before. I didn't change anything. I just changed the added the subscript I here. So all the xy's become xi and yi's. Okay, so this is the face I here. So first Alice shows this yi and send to Bob, and so the adversary may change it to yi prime, and then computes it's ri and ri prime. And then and Bob chooses wi prime and send it to Alice together with the tag ti prime computed using ri prime. And Alice checks if this MAC ti, if the MAC ti she receives is correct. If not, then she rejects. Otherwise, they compute the output zi, which is some extractor applied to x, and wi and wi prime. So this is exactly the same two-round protocol as before. But if you think about then the protocol may fail because here the xi may have small entropy. So the entropy rate may be smaller than half. So the previous two-round protocol may not work. Basically, the MAC with KRI may fail. So what are we going to do? This solution is that, so remember when we first reached the phase of the first good block, we already have, at the end of that phase, we already have the two parties agree on some uniform random string. So we can use that shared uniform random string from previous round to construct another MAC. So this zi prime minus 1 is the output string from the previous round. So we use it to construct another MAC. And then we also use this MAC to authenticate the message W prime. So here, instead of using just one MAC, we will using just one MAC. We will use another MAC to authenticate this message W prime. So this seems to be good, except we have another problem, which is that the MAC of the constructed using this RI here may leak information about this string zi minus 1. But the solution is that, as we have seen, that there are MACs that are resilient resilient to leakage, even if the university knows some information about the MAC zi minus 1. As long as the leakage is not too much, as long as this zi minus 1 still has entropy rate greater than half, then this MAC can still work because it's a leakage resilient MAC. Okay, so here this is a modified protocol here. So again, this is the same two-round protocols. I didn't change anything. Okay, so now I'm going to add another thing that they have output from the previous phase, the -1 here. So this is a round after the this is a phase after the phase of the first good block. So the two parties already share some uniform random, probably random outputs from previous rounds, the -1 here. And then instead of just using this MAC to authenticate Wi prime, we use another MAC, which we call Qi prime, which is this MAC, this LR MAC, which stands for the leakage resilient MAC. So we use this Zi prime, Zi minus 1 prime as a key for this leakage resilient MAC to authenticate Wi prime to get another tag Qi prime. So we send both of these tags to Alice. And of course, Alice can get some modified version WTQ. And then Alice, instead of just checking one MAC, she will check both of these MACs. and she will reject if either one of these does not hold. Otherwise, they will just compute the output Zi as before. Okay. So now, if you think of it, then it's very nice. So at the end of the protocol, at the end of the phase for the first good block, the two parties end up with some uniform random string. And then this will guarantee that in the subsequent round, they will also end up with agree on some uniform random string. And then in the next round, they can use this AI, and then they will again end up with some agreed uniform random string. And this keeps going on until the last phase. Yeah, sure.
So to check for the leakage resilient MAC means that it's still secure even if the key is not completely.
Yeah, even if the key is not uniform but has entropy rate greater than half. Yeah. Yeah, right. So basically, the only thing that the adversary can know about this Zi prime, Zi minus 1 prime is this Ti prime thing. Because these Y's, these W's, they are all independent of this thing. So we can set the tag, set the size of the tag to be smaller than half of the length of the minus 1. Then this leakage resonant MAC will guarantee that Bob can authenticate this WR prime to Alice. Okay, so we're almost done. However, there is one little subtle problem here. So the problem is that the Eve may not behave synchronously, which means that he can talk to Bob many times before he talks to Alice. So in this case, so the Alice and Bob may not have a synchronous view of the protocol. So they may not use the same Zi or Zi to construct the MAC, which causes a problem of the protocol. So the solution to this last problem is that we can add a live list test for both parties at the end of each phase. So basically here, when Bob sends WI prime to Alice, he will also require a response from Alice by applying some extractor, a strong extractor, to X and WI. So Bob will check this response. So if this response is not equal to his output, then he will reject. And when Alice sends his response to Bob, he will send also her own challenge. This is this VI. And Bob will also compute the response and send it to Bob. And send it to Alice. And Alice will also check. And if this response doesn't match, then she will reject. So this is basically saying that if Eve tries to talk to, say, if Eve tries to talk to Bob many times before she talks to Alice, then Eve will not get a response from Alice. So she will have to come up with a response, fake a response from Alice to make Bob go through this response check. But then that can succeed only with very small probability because it's a strong extractor. So the response thing, if Eve does not know X, then this thing is completely uniform in Eve's view. So the probability that Eve can come up with the correct response to Bob without the response from Alice is going to be very small. So in that case, Bob will reject with high probability. So in this case, by adding this naive list test, we can make sure that the protocol actually behaves synchronously as we want. Yeah. Okay, so that is sure.
Does this live list test thing help even before you get to the first good round, or you just don't care about it?
What's that?
So if once you've got the first good block, so the first good round, then I see about the liveness test help? Does it also help sort of before you get to the first quick block?
Yeah, you need to do the liveness test for every phase to ensure that the two parties behave synchronously. Yeah, they are in different blocks.
Same block.
I see. But so if WI isn't random, or if we're not in a good block, can we still guarantee that WI is?
Well, WI prime is chosen from Bob's own private local randomness.
Okay. Thanks.
So yeah, just by adding this liveness test into our previous protocols, so that gives our final protocols. And right, because in each phase there is only like 2 rounds, something like that. So you get a constant number of rounds because you have a constant number of blocks, and because each of these things they have a so the size of each of these messages is something like s plus log n. So the final entropy loss is only order s plus log n. Okay. Yep. Okay. So that is our final protocol, and here's some conclusions and open questions. So we construct the first non-malleable extractor for entropy greater than n over 2. So of course, the first open problem is to construct non-malleable extractors for smaller entropy, say delta n, or even n to the delta something. And just note, we recently get an improvement that we can achieve. We can construct the non-malleable extractor for entropy rate slightly below n over 2. It's something like say 0.49 and something like that. But it still remains open to construct non-malleable extractors for any constant delta here, or n to the even n to the 0.9 would be very big improvement. And then the second result is that we get this constant number around privacy amplification protocol for the case where k equals to delta n, and it'll be interesting to get the number of rounds down to 2 rounds. In that case, we'll get the truly optimal protocol. And then again, even if we can get a constant number on the protocol for the case where k equals to n to the delta, so even n to the 0.9, that would be a very big improvement over previous results. And that's all. Thank you.
I have one question. So, is it easy to construct, or I don't know, is there some way to construct a non-malleable extractor outputting many bits from a non-malleable extractor outputting 1 bit by increasing the seed length?
Right. So that is actually related to another. So we have another improvement actually here. So as I said, right. So here, so this result by coherent resonance gap, they have the output is smaller than seed length. So we have another improvement that we can somehow, by giving this kind of a non-malleable extractor that outputs a small number of bits, we can use some other kind of tools to get it to output a large number of bits.
I see.
Yeah, but that's still only that still needs that this output to be at least log n. Yeah. So if you want to use a non-malleable extractor that outputs just 1 bit to convert into a non-malleable extractor that outputs more bits, then that is still open. We don't know how to do that.
And also, what happens if you, so you have this protocol for entropy loss, say delta n, right? And that you achieve by splitting up to constant number of blocks.
Right.
If you split up into super constant number of blocks, what happens? You probably will not get better results than the existing ones, but you can still make that protocol go through.
Right. So actually, our protocol, we have this constant number around protocols for k equals delta n, but we can actually get something slightly sublinear, but then we wouldn't get a constant number of rounds. We would get, and the entropy loss is not optimal, but it can still be better than s plus log n squared. But that's only very slightly sublinear. If you go beyond a certain point, then the number of rounds would blow up to polynomial or something like that.
What's that minus 1 OW?
What? Sorry?
Otherwise.
Oh, otherwise. Yeah.
Thanks again.